calling you. The universe is calling me. It speaks both day and night. It's full of dark and light, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's home. Boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Hey everybody, welcome to SkyTour Livestream. It is I, Mark D'Antonio. Tonight we're going to do something a little different. We have been fighting a massive front out west, so it's not clear enough out there for us right now. But tonight I thought what we might do is do some experiments and show you visually what would happen if Apophis struck the Earth, if the Earth had rings, if we had more than one moon, if we were hit by other things, or if Jupiter collided with Saturn, or I mean, all kinds of things. We have everything under the sun. And I'm working on this. I've been working on this for a while because I wanted to show you just a few little concepts. This application we're looking at right here is called Universe Sandbox. Universe Sandbox is a physics simulator. It takes into account the accurate physics, the accurate atmospheric physics as well, so that if you strike the Earth with an asteroid, the Earth heats up, and you see that. You see the Earth go into runaway glaciation when we get a pall of dust that's in the air around the Earth from an asteroid strike. And depending on if it strikes in the water or strikes in the land, we get different effects. Massive tsunamis are visible. You can actually see how they radiate out from the source of an impact. It's pretty cool. We're going to see all of that tonight. And because you guys are in the chat, I want to welcome you all. I just wanted to welcome you and tell you that if you've got ideas for what you'd like to see happen in our solar system, then why not go ahead and put them in all caps. This is when you can. People always say, don't yell at me with the all caps. You can put all caps here if you're asking a question or if you want to see something, because I'm doing this right by myself right now. So that's okay. Usually the cloudy night streams I do myself. I don't want to burden anyone with trying to figure out things to say. But I think it's interesting, and what I'll do is I will take you through this. One thing that I'll do right first is just show you this simulator. Universe Sandbox is a beautiful simulation of our solar system. And as you can see when we scroll out, there's an awful lot of things out there in our solar system. Notice that one of the objects that's whipping around here, this one right here, this is a outer world way out in the Kuiper belt called Sedna. Okay, this is an approximation of what it looks like. We don't really know what Sedna looks like, but this is on the right here. You'll see it. This is what we think Sedna looks like, and you can spin this around and kind of see. It's probably a very icy world. We do know its mass. Okay, in terms of mass of the Earth, it's 0.000302 times the mass of the Earth. It's really, really small. And as far as its radius, it's only 7/100ths of the radius of the Earth. And we can change that radius. Let's put it in kilometers. The radius is 477 kilometers. Now, that's radius. So that means that the diameter is over 900 kilometers in size, just so you know. Okay. So it's pretty cool. And out here where we are right now, it's exceedingly cold out here in the Kuiper belt. And, we can be way, way far out. And we'll still be before the Oort cloud, the realm of the comets. So as we come into the inner solar system here, we go through the outer solar system. See all these objects here flying around? We're seeing the orbits of all these many different things. And the reason that we're seeing them is because these guys are actually what are called scattered disk objects. They exist out here on long elliptical orbits, cranking around out there beyond the outer solar system. Okay, Makemake is an example here. Makemake is sort of a icy world that exists out here as well. And it's, again, as you can see, we bring its data up here. It's also very small. It's only 9/10 actually of the radius of the Earth. So it's just under half the Earth in size. So it's actually quite well under, right? So it's literally about 1/10 of the radius. So it's really, really small. All right. Again, bring that in kilometers. You can see that it's 572 kilometers in radius. So 1,000 kilometers, 1,100 kilometers in diameter. I want to spend some time thanking everybody for coming in and say hello to everybody. Calabos was here first. How you doing, Calabos? Calabos, as you know, and Tiffany are two of our most wonderful volunteers for SkyTour Livestream. They've officially become volunteers for us. We're so proud of them. Let's thank them and make them feel at home. And they're actually helping us with things. They're actually the ones that have come up with and are distributing equipment that they exclusively give away on this particular channel. Not a bad thing. And in an effort to help other people look out there and see what's up there in the sky, well, it certainly helps to have an astronomer around. That's me. And helps someone who is willing to give away equipment they can afford to, and that would be Calabos and Tiffany. No, they're not millionaires. What they are are dedicated and passionate people that want to see everybody, all of you here in the chat. They would love to give every one of you binoculars. I know they would. We've talked about this. They would love to. If they could, I know they would have already. But working within the limitations that everybody has these days, we go through and we produce little contests with them. And in our streams, sometimes equipment is given away. And we leave that entirely up to Calibos, whose name is Mike, by the way. That is something that I think we would be pretty cool to do. Now, what I would do is say this, too, and I will extend the offer to Calibos. You are free at any time to come on board with us and join us for the live broadcast. You just have to tell me if that's what you want to do. Because if you'd like to, I can endeavor to bring you in here and see if we can get you live with us on the air. And that is entirely your call, Mike. I'm happy to announce, though, that Mike and Tiffany will be at Contact in the Desert. I will also be there. And I'll be doing not one talk. I'm going to be doing a lecture. I'm going to be doing a workshop. I'm going to be doing a SkyTour live stream from there, live, opening the observatory from there. And then I will be going with Ben Hansen and doing his Skywatch with him. And Ben and I have been good friends for many years. And, people love what we do and love what I do with SkyTour. I'm so happy. I'm actually humbled by it. I've never actually been so surprised as to see how many people really love what we do, and just made me crazy just thinking about it. And while I'm here, I want to say hi to Renee Cruz, who was the second one in. Michael Hedrick is with us. Jessica Smith. Hi, Jess. How are you? Nice to see you. And we have Suzette Bavier. Hi, Suzette. Nice to see you. And Renee, she's always got those wonderful icons. She just loves space and UFOs and aliens and so forth. Tim F. is here as well. Genghis, Alicia Vieras. Hi, Alicia. How are you? And Darlene. And, of course, your amazing husband, who has like a perfect beard. He has the perfect beard. It's incredible. He takes such good care of that, So, Anahata 77, Bonnie's with us. Donald Kunzer, hey, man, how are you? And Cosmic Ray, hey, man, what's happening? Johnny Peppers. I've known Johnny Peppers for a long time. Okay, he in Facebook, but he is a really cool guy, so say hi to him. He comes in once in a while. This is kind of rare to see him here, so let's all welcome him and say hello. Johnny Peppers. All right, and Rascally Rabbit's with us. Stuffy's here. Hey, Stuffy, how you doing? All is going well. Got my water, so I'm covered, And let's see, besides Rascally, I know we had someone else in here. Oh, Michael Hedrick, sorry, man. Yeah. And Michael Hedrick says he's finally getting his glasses that he needs, so this is good. That's fantastic. And then we have Blind Eye Mitchie. What's going on? Nice to see you, man. Welcome to the stream. Keep in mind that if you haven't subscribed, if you want to take part in any of our equipment contests, you have to be a subscriber. And that's easy because, very easy, because of the fact that it's free. You just have to just hit subscribe in our YouTube channel, and then you just have to, hit the bell to get alerted. And when you do hit the bell, it's actually a drop-down box. Drop down the box and click all notifications. So then you'll know. That's how all of you got here, so that you see us now, because you've been looking for us or said, hey, what's this? Hi there, Mindfork. That's Chris. Chris is great. She's an amazing lady. I met her several times now. She has the energy that like of 10 people, okay? And that actually works very well for her. So she's great. So I was glad to see you. So anyway, I think, and Sam S. just joined us. Hey there. So let's do this. Let's first look at something that I wanted to show you. This is very important to understand. here we have the planets going around the sun. Here they are. See them all? There's Jupiter way out there. Saturn's beyond that. Okay. And then we have Uranus up there, and then Neptune way out here. And, of course, our good friend Pluto way out here. Now, these planets all have mass, right? If we zoom in on the sun, you can't hear it, but it's making a low rumbling sound. I really love that part of it. Okay. And now, if we zoom out a little bit, you notice that you see what looks like a path. That is the motion path of the sun. Now, this is a physics simulator. It's going to show us exactly what physical effects would be and how the Earth's orbit would change if we added another planet in the middle. All kinds of things. And so one of the things that you'll notice about the sun is that it's going on a weird path. Now, I'm going to accelerate time here. Okay, I'm doing it now. I'm going to accelerate time, and you're going to see the path of the sun changing. Look at that as it goes through space. Now, when I do this, okay, you see the planets whipping around, because what I'm doing is I'm going literally 4 years per second in our simulation here. But you'll notice that the sun is leaving this weird path. What's it doing? I thought the sun was solid, right, and steady in the center of our center of our solar system, our local universe. Why is it doing this? Primarily, it's doing it because it's reacting to Jupiter's pull on it, right? Because everything that's in this solar system actually exerts a gravitational pull on the sun as well. Jupiter is the largest planet and by far the biggest actor in that process. But Mercury, Venus, Earth, and Mars all tug on the sun to some extent. And all of it adds up to this really funky corkscrew path that the sun takes as it makes its way around the galaxy every 230 some odd million years. All right. So that's pretty cool. So now that we've got that out of the way, why don't we take a look at the different planets? Let's visit Mercury first. Okay, as we go to Mercury, you'll see that bringing up the panel for Mercury here shows us its mass in terms of the mass of the Earth. It's only 5/10 of the Earth's mass. Okay, or 5/100, I'm sorry, of the Earth's mass. And then it's only 0.4 times the radius of the Earth. Okay, so now the average temperature is 156 Celsius. Now that's actually the average temperature, 315 Fahrenheit. Now that's taking into account that there's a side of Mercury that's unlit at any one time. Okay, so right now, okay, because we're focused on Mercury, that is our center of focus. Okay, so if we zoom in, we'll zoom into Mercury. Here we are. Okay. Yeah, that's Mercury. And actually, those maps are pretty cool. On the surface of the planets, they're actually quite accurate. So now, if we zoom out again, right, one of the things you'll see is that it takes 88 days for Mercury to go around the sun, and that is 2.89 months. Now, if we go down to days, okay, you'll see that its orbital period is 87.9 days. Okay. However, you'll notice also that its rotation period, how long it takes for it to spin one time on its axis, isn't 88 days, it's 58 days. What's going on there? See, Earth and Earth and the sun are not tidally locked together, but Mercury and the sun are somewhat tidally locked. Like the moon has one side facing us, that's tidal locking. And tidal locking occurs in the solar system as well with the other planets, like Mercury. Mercury is somewhat tidally locked to the sun, but not quite. And so it has to go around one time in 58 days, and then every 88 days it goes around the sun once. Pretty interesting how that all works out, you know. Now, I told you to put in all caps, and I didn't miss Donald Kunzer's question. He said, "Hey, Mark, I read somewhere that Earth has a second moon." That is correct, Donald. There's a second moon going around the Earth. It's in a very odd orbit, It's actually not in this simulation. I actually looked for it before we started today because I knew someone was going to ask. And it's a great thing to ask. Considering that the Earth has that second moon, what is it? It's actually a small asteroid. Now, there is some research indicating that that asteroid, that small little asteroid, could have been a remnant of the initial collision that created our moon that we have. And so it was something that was put into this elliptical, strange, shared orbit. And it's actually only temporary because we can project a time when it's going to escape that orbit and end up in another orbit all its own as a near-Earth object. Pretty cool, you know. So, Ricky Ricardo says, full Wolfman Jack moon tonight. All right, hey, Wolfman Jack here. I remember Wolfman Jack. If any of you remember Wolfman Jack, you're as old as me. So, that said, let's pull away from Mercury because it's really too hot. And we'll go to Venus, all right? The next planet out. If we jump out to Venus here, okay? Venus is rather featureless. I'm spinning it up here, but you can't really see any change. However, in different light, that is in ultraviolet light, you'd see that beautiful, those beautiful chevron clouds that Venus is famous for. The chevron clouds every so often on Venus. I have a model in my shop that I did for NASA's Unexplained Files on Discovery, and it shows a bland Venus just like that. However, when you put an ultraviolet lamp on it, all of a sudden you see all this detail in the clouds that shows up just like the real thing. So that's actually pretty cool. So neat stuff. Eric's Automotive, how you doing? Good to see you. By the way, if I didn't say it before, Ricky Ricardo, nice to see you. And so, let's see. Darlene said that she had a problem because Pluto was no longer considered a planet. Yeah, well, guess what? You can tell Darlene that I have the same problem. Okay? Because I do believe Planet 9 is Pluto. Now, Planet 9 was found by a little tiny guy. He was like 4'9", 5 foot tall. And his name was Clyde Tombaugh. And I met Clyde and sat on a grassy knoll with him up in Vermont, in New England. He was speaking at an astronomy conference up there. I was attending the conference at the time. And I sat with Clyde and I talked to him about, what it felt like to be the man who discovered the 9th planet. And he said it was the most amazing feeling to know that he could contribute to astronomy. Why do I say that? Wasn't he an astronomer? As a matter of fact, he was not. Clyde Tombaugh was a self-taught astronomer. He never went to school for it. Yet there he is, making discoveries that affect all of our lives. Isn't that incredible? So, even if you're not an astronomer, the universe is still open to you, and there's still things you can do. So, and as far as moving to Earth, well, I'm going to show you something as we move to Earth. Okay, we'll bring up the Earth's plate here, and this information, all all about the Earth. Okay, the average temperature on the Earth, believe it or not, is 47.9 Fahrenheit. That's the average temperature. That doesn't mean it's the temperature everywhere. All right, you can see above there that Earth is mostly water, right? So it's also life-bearing, obviously, because we're all talking. 4.5 billion years old. And the nice thing about this is that if we zoom in on the Earth, okay, now right now I don't have the moon attached to the Earth. So what I'm going to do is I'm going to add the moon by coming down here and saying add the moon. Well, there's the moon. Now, Earth is moving around the sun, as is the moon, but the moon is also orbiting Earth, so that accounts for this weird-looking orbit here, okay? Now, what's interesting here, I got to show you something, all right? If we come to the plane of the orbit, the plane of the solar system like this, okay, that's about right. I want you to watch where the moon goes, okay? Let me put it, where's the sun right there? So I'm going to put the sun right here, okay? There we go. Okay, now watch the moon as we accelerate time here, the moon goes up above the plane of the solar system. See that? And then you'll notice something else. It comes back down, right there, and goes below the plane of the solar system. Now that amount is 5 degrees above and 5 degrees below. And you'll say, well, wait a minute. What's going on there? Is the moon not orbiting directly around the Earth like the Earth goes around the sun? Correct, it's not. It's at a 5-degree inclination. Now that could have occurred because of the original manner in which the moon was created, through violence, okay? Or it could have occurred through some other means. Most likely it was an origin orbit creation. Now, this also points out another reason why we don't see lunar eclipses every single lunar cycle. Okay, you see here it's above, and it goes a whole lot of distance before it then crosses the solar system plane. All right, so right there, it crosses the solar system plane. All right, so if you were to, and the other thing is, it's a little bit of an elliptical orbit, slightly elliptical, and it's on that angle, it's on that slant, like I told you. So what happens is that whole orbit precesses, meaning that point where it crosses the Earth's or the plane of the solar system on one side, then the other, that continues to move. It moves. So it precesses. That point where it crosses keeps moving. All right? And at the point where that point crosses between the Earth and the sun, okay, that's when we'll get a lunar eclipse. At the point where the moon will cross, the Earth's orbit in the orbit of the main orbit, the plane of the solar system, exactly when the sun is there. And when that happens, we get a wonderful lunar eclipse. And that's the coolest thing. All right? So that's how eclipses, lunar eclipses, work. Solar eclipses, of course, are when the moon is actually crossing in front of the sun as seen from the Earth. And that happens when the moon is on this side, and also when the crossing point of the moon to the Earth's orbital plane are lined up with the sun and the Earth. When that happens, okay, that is when we'll see an eclipse. So that's why we don't see them every single time the moon goes around the Earth. If it was at the same plane, we would. It'd be once a month we'd see an eclipse, but we don't. Now, in the chat, we had Rascally says April 2024. Yeah, April 8th, 2024, all right, coming up, is a total solar eclipse. Now, here in Connecticut, it's going to be a partial, but there's a band stretching from the American South, Central South, all the way up to the Northeast of totality. And so that's going to be pretty cool. Old Schooldy says, wouldn't it be influenced by the tilt of the Earth? Are you talking about the moon, Old School? Let me know. Michael Hedrick says, Mark, is Betelgeuse back around the sun yet? Is it blowing up yet? Yeah. Actually, no. Betelgeuse is out in the open right now. Actually, it's past the meridian. So by like 9 p.m., 9:30. And so Orion is actually getting lower into the west, but not yet. We'll have plenty of time to explore it. All right. But I did want to show you something else. I've been working on another piece of equipment for the observatory, and I'm going to show it to you because I do have it here, and I think that you might like to see it. Let's go see if I can bring that up. Is it here? Uh-oh, where'd it go? Hang on, let me see. Oh, it might be here. It might be this guy. Yeah, just a sec. Yeah, that's it. Okay. All right, I'm going to show you something in just a second here. Okay, let's go see now. Oh, there we go. Okay. And go. Oh, that's me. Go. There we go. I've been working on an all sky cam, and it's finished. And so this all sky cam here, now it's raining here, so this is why it looks this way. But it tells you the date, the time. It's the STLS all sky. It's a replacement for what's out there. It's full color. This back here, that's my house. That's the stack for the wood stove. And when it's lit, you'll see all kinds of smoke coming out. This is just a test setup for us right now. But let me show you what it's capable of. So let's go back to here. And I'll show you by showing you a time lapse. Here's a time lapse that I shot with it. Okay. There's the clouds. That's my house, yes. Now, I didn't have a way of getting it out of the screen, so I actually sliced open the screen. Don't tell anybody. Don't tell anybody. Okay. All right. So now, as the clouds begin to move away, you'll end up seeing the night sky. And it's a high-res camera, so it really is outstanding. And you'll see here in just a sec. All of a sudden, the skies part, and we see the beautiful starry sky begin to appear. Okay, let's stop right there for a sec. Here's Gemini, Castor and Pollux, the Gemini twins. Here's the one side of the constellation, here's the other. And it comes up here, and you can see a little faint thing right there. That's Messier 35, the cluster that we look at very often. Okay, here's the Hyades with Aldebaran, that red star right there, the V shape. The Pleiades are they're just out of sight here from this, but you can actually, in the images, you can zoom in and see, for instance, the Orion Nebula. It's absolutely amazing. Right down here is Orion. You can see, let me get that on there. Okay, you can see the Orion Nebula right there. It's in that, right in the bar. See the belt of 3 stars? Actually, I'll just do it this way. A belt of 3 stars. Let me grab it here. There we go. There's the belt of 3 right there, and there's the Orion Nebula. Zooming in on that, you can see the red nebula. It's actually visible and obvious. So this is a incredible upgrade. Imagine this under a gorgeous Milky Way sky. This is a somewhat light polluted sky, as you can see here. Right here, you can see light pollution up here. Okay, but let's continue so you can watch. Okay. So right now I'm taking an 8 minute exposure. An 8 second exposure. All right, and you'll see occasional planes flying through, and satellites actually, a couple of meteors blasted through, but not a bad sky for where we are. This is 1 in the morning when my son returned home from the TV station. Okay, so that's where the lights were. All right, so now you get a good feel. This is going to be the next all sky cam, and I'm installing it next month. So this is going to be just a beautiful addition. All right, frame rate to Donald Kunzer, who asked. As I said, I'm actually letting it decide how long to make the exposure. So you can see the exposure right now is 10 seconds at a gain of 250. All right, so moderate. I mean, there goes that was a satellite right there, blasting by. You saw that. Okay, so it's just before the sun. As the sun's starting to rise, I got to show you. Okay, right. This is going to be part of the spring sky that we're looking at, and if we take it back, let me just leave it right here for now. This is Arcturus, and this is the kite shape of Bootes, the herder, sheep herder. Okay, and then we have Corona Borealis right here. Okay, that ring, corona, or the ring crown. Okay, and then we'll have Hercules over here coming up. But later in the season, it'll show up better. Coma Berenices. Right here, you can see that very faint patch of stars. So it's actually really, really nice. I'll back up just a bit so you can see a little better. All right, that's quite a bit backed up. So anyway, you get the idea. So this gives us the wonderful thing. And the nice thing about this is this will run during the day as well and will allow us to see daytime imagery as well. So if something happens during the day, we'll catch it. If something happens at night, we'll catch it. It's really quite cool. Okay. This right here is the Big Dipper's tail right here, the Big Dipper. The handle, so to speak. Here's the bowl. It's in here as well. That handle points right down to Arcturus, which is right there. Okay, so that's how we find Arcturus. Follow the handle and continue, and you'll find it. Cool, huh? All right, so that right there, that is how we're going to be utilizing our newest edition. All right. And I'm looking forward to being able to use that during the day as well. That's gonna be really cool to use it during the day out there. All right, let's see. Now let me see what I missed in here or anything. Okay, hey, Kyle's here. Kyle Lynch. That's Lynn Beats. This cosmic ray ass is at 180 degree lens. No, it's 150. But the All Sky program cuts off the top and the bottom right now, so I have to figure that out. I might change the lens, but I like this particular lens because it allows me to see color rendering of the stars quite nicely, and it allows me to see the other attributes in the sky very well, like faint clusters and things. Not sure if a wider angle lens is going to give me that. But you see almost 180 degrees, well, 150 to left and right, and it cuts off the top and bottom. So it's not that big a deal. But it's really nice. All right, so let's see what else we got. And then we're going to go start throwing things at Earth. Okay. All right, Izabela's here. Hey, Izabela. Nice to see you. Okay. Lynn Beats asks if we can create a sim of test object of interest 5747b. That would be cool. Is that the planet that you discovered, Kyle? Let me know. I bet it is. And actually, yes, we could create a simulation of it, actually, Kyle. All right. So let's do this. Let's go into our Earth right now. And let's go onto the sun side. And as I start it up again, you'll see that we're moving pretty fast. We're actually moving, and where you see that is down at the lower left here. It says 1.04, it's 1 day per second. So if I slow it down a little bit, okay, now we're doing 1 hour per second. All right, and that's actually pretty cool. Now you can't even see that yet, and let me see if I can help you to see that a little bit. I'm in the way, so I apologize for that. All right, let me let's see if I can move myself over. Oh yeah, I can. So you can just do that. The time is right here, so you're not gonna be able to see it too well, but it's right there. Sorry about that. I'll just tell you what it is. All right, we're doing 1.5 hours per second right now. So what we're going to do is this. I'm going to take us and I'm going to take an asteroid that we've been all concerned about, and I'm going to see if I can make it hit the Earth. And I want to show you, I can't make it hit the Earth, I've done this, but I want to show you what would happen, and the ensuing physics that takes place is really absolutely incredible. So we're going to go here, we're going to say plus, and we're going to go to minor planets. All right, and we're going to say Apophis. And we're going to bring Apophis in, and we're going to launch it at the Earth. Okay, now if you look down over there in the lower right, okay, this you can see. It says its launch velocity is 3.71 kilometers per second. That's a little slow. It's going to be more like 11 kilometers per second, right? So we're going to leave it at 11, okay? And now we're going to launch it. We'll launch it here, all right? And as we launch it, okay, notice something right away. Apophis is tiny. Apophis is really small. And if we just go zoom in on it, okay, sorry, let me grab Apophis and zoom in on it. Apparently, I gotta grab it better. There we go. So you zoom in on it, okay, and this is what Apophis looks like up close, right? It's just a not what's called a notional view of it. We don't know really what it looks like, other than what this looks like here. But again, it's 1,722 feet in diameter. Not big, okay? That little tiny thing, which you can't even see. You can see its shadow. And watch the impact. Ready? I would not want to be where that shadow is, coming converging. But watch this. All right? As it strikes the heart of Africa, right? Pow. So it strikes the heart of Africa now. And now we're seeing this strike take place. And you might say, oh, we're safe over here on the other side of the world practically. But not so. Because look what's happening. It's throwing up a debris cloud. A massive debris cloud. And guess what? That debris cloud is coming back down. Much of that is the Earth from African soil being blasted up into space. All right? Where it hits nearby, it superheats the planet right there. If we bring up the Earth here and we get our graphs out, you can actually watch that occur, right? Okay, there is the gas pressure. There's an overpressure, very, very high pressure right at the impact point. The temperature on the planet, okay, right now, we'll go to degrees Fahrenheit here, 64.5, all right? And now, look how far out into space that 1,700-foot asteroid blew debris. Now, we can accelerate this, and you can watch it come back. So I brought us up to about an hour per second. So far, everybody's okay in the United States, right? But look what's happening. Look what's happening. A strike by Apophis could literally be an extinction-level event. Okay, look at this. Now the Earth's gravity takes over. Strikes have started in South America. Okay. As the United States is starting to wake up, something hits off of Nova Scotia. And now up there, Nova Scotia, here comes another piece right here. Where's that one going to hit? Oh, man. That hit like right, holy cow. And then up here in Canada. So no place is safe, see? And these are extremely, they're hot, large pieces of debris. Each one is going to make their own crater as it strikes. So something like this is really bad, okay? And that's just Apophis, 1,700 feet, 1,722, okay? So already away on the other side of the world is the Hawaiian Islands here. And you'll notice that we've had two strikes right here. Well, guess what they're going to generate? Tsunamis that are going to inundate the west coast and then part of the Hawaiian Islands. They may not be that large, okay? Depends on the size of the debris. But let's back out. Check it out. Earth is a maelstrom. And I'm accelerating time now so you can watch. Earth's own gravity is its worst enemy. As all these fragments strike the Earth. All right. Now what's happened is you can see all the strikes here in this lower diagram over here. Right there. You can see some, and some large ones right there. A big one struck right there. Okay. So it's actually pretty bad. And this is just a few days later. All right. So you say, oh, well, we survived that one. Okay, maybe so. But could we survive another one? what if we weren't struck by Apophis? What about Shoemaker Levy 9, the comet that struck Jupiter? Let's see what that would do. And again, about 11 kilometers per second. I'm going to slow down time again for the launch. Well, Shoemaker Levy 9 is also small, okay? And it's going to be, let me get out of that mode. Shoemaker Levy 9, let's grab it. I have to grab it. Do it this way. There we go. Its radius is basically 351 meters. Okay. So, 1,000 feet across. A little more. All right. So let's watch what happens when Shoemaker Levy 9, that Jupiter just ate up and spit out like nothing. Let's see what happens here. Hey, Lubo. How you doing? Welcome to you. Fantasy. Hi. Okay. Uh-oh. Here it goes. It's going to hit right off. It's southeast of the Yucatan from where Chicxulub was. Okay. But now watch. Let's watch carefully and see if we can see the shock waves. I know we can with the higher impacts. Okay. Well, let's just speed it up a little bit now. Okay. Shoemaker Levy 9 is mostly ice. So the way it strikes is going to be different. But you'll notice, this is quite a kill zone here. All right. And again, much of that material is material from the Earth itself. Florida's been hit multiple times in north of Orlando, south of Jacksonville. Okay, Chicago's gotten blasted very badly, and as you can see the shock waves moving. By the way, see the shock waves? All right, that's a real-time calculations being done of the shock waves. All right, so that's Shoemaker Levy 9, and let's accelerate time. So over the next few days, the Earth will absorb these shocks. All right. So it's actually pretty heavy duty impact. Okay, so now you don't think we're going to just rest with that, do you? No. Let's take something else. Let's take the asteroid Vesta. All right. And we're going to launch that at the Earth as well. All right, so here we go. Now, that's not actually the right shape for Vesta, by the way, just so you know. Vesta's more oblate and flat, right? Not flat, but kind of like a more of a oblate. I've actually got a model of Vesta here somewhere. Let me see. Let me pause for a second. See here. Oh, here it is. Yeah, I got Vesta. I 3D printed this to show you. So let me come back over here. All right. So this is Vesta, right? Yeah, okay. Mark, make sure we can see it. Yeah, hold on. Let me show the background for a split second here. All right, here we go. So here's Vesta. Okay, kind of looks like a walnut, doesn't it? But this is actually taken from the USGS data and the NASA curated data that I got. And I printed it out so you could see it. So that's what we're looking at that's going to hit our planet. All right, that's what we're making a model of. That's what we did a model of, so that's what you'll see. All right, so let's get that off now so you can see through me. All right, now, when we talk about Vesta, what are we actually talking about here? We're talking about a planetary body, a minor planet, right? And Vesta is actually a very, very small mass object, right? But its radius, okay, its radius is actually, it's 252 kilometer radius, okay, so over a 500 kilometer diameter. So we're talking about a hefty object that's about to strike the Earth here. And this is why it's so good that Jupiter has swept these objects out of our solar system. All right, so we're actually moving now. I'm going to... This will be interesting because I'm going to show you something. As Vesta approaches Earth on a collision course, I'm going to do something crazy. I'm going to stop it right here. Okay, let's do this. Okay, this is real time. No, I'm not going to make you sit through this. But this is real time. So you'll see that Vesta is hanging in the sky. Death and disaster are coming. And there's nothing anyone can do about it. Central Africa is going to get destroyed. But how much will it take out? Will it take out Africa? Will it take out Saudi Arabia? How about India? Will it take out the United States on the other side of the planet? This is a 1-to-1 speed. It's moving, right, by the way. This is actually in real time. See how it's moving? Yeah, the universe can be just awfully slow. And it's killing me slowly is what this is. So what I'll do is I'll just accelerate it. I'll do... let's do, this is 5 seconds. 5 seconds pass for every second of real time. Yeah. So now, if you're in Africa, right, you're going to watch a shadow approaching from the west. And it's coming, and it is just, it's the killer shadow. Because this means if you can see that shadow, you're done. Now, as this enters the atmosphere, you may or may not see it. You'll see a bright light, but you may not see it because the blue sky could actually prevent you from seeing it because the sun's on the other side. So it might actually be very, very faint in your sky until it begins to burn up in our atmosphere. Notice now the collision has already started. Over here, the data on the left. And you can see the shock waves starting to move out. Oh, gosh, to actually see something like that. What an awful slow motion death that would be. Yeah. The largest chunks now would actually come off. Now, we'll see them here if we speed up a little bit. They're starting to come out. And here the shockwave now moving across Africa. And it makes a cute diamond pattern. No, it doesn't. That's actually just an artifact of the geometry. But look at that. This shockwave, accurately shown, it's a compression wave. And it's actually causing the air to condense all the way around. Okay, kind of like when a plane goes supersonic, when you see a Navy plane go supersonic or you see a nuclear explosion, you'll see a shock wave and there's a condensation front all the way around. And that represents what's called overpressure. And overpressure is pressure beyond the normal 1 atmosphere that we feel. And that overpressure is actually something that could burst your lungs because it's so powerful. These things would look like they're pausing in the air for a great long time, about to rain death down upon you. So if we accelerate this a little bit, as you accelerate, by the way, the physics it loses accuracy. They do compromises. Look where it's striking in the water. You see all this spot? It's actually going all the way to the bottom, striking the bottom, and literally carving away the water in the initial splash. Then that water moves back in, and it generates tsunamis. So now on the other side of the earth, everybody in the United States, they might say, wait, I thought I felt something. Did you feel something, Mabel? No, I didn't feel anything. Well, you're gonna, because now the particles, as in giant rocks, fragments, start re-entering the Earth's atmosphere. Look at that. California's gone. Okay. The East Coast just got slammed with this major tsunami that could be up to a mile in height. Okay. I'm at about 1,000 feet here, and the water from that tsunami, I'm about an hour from the shoreline, and the water from that tsunami would reach me. So these are massive. I'd see the wall of water right from here. That's how high they'll go. So you can see Earth is under an extinction level event right now. So we back out and say, well, look at that. Our planet's was such a nice place to live. However, as always, Earth in general will shrug off impacts like that and will continue. Not in the same way, not looking the same way, but it will continue. Okay, so, but you can see that the Earth has been reshaped. If we look in the upper right here, okay, continental shapes we don't really recognize now, right? There's the United States. Florida's shortened, and we've noticed that South America has literally lost a giant chunk of itself here. There it is. So there's a lot going on. Okay. One thing also to notice is that the North Pole and South Pole are gone. And if we consult our diagram over here on the left, you can see why. The temperature on average, the highest temperature is 330 degrees Fahrenheit. And the average temperature is around 142. And the lowest temperature is minus 38. And that's at the extreme southern reaches right now. So this is actually, the physics is actually quite accurate. Johnny Peppers says, could you show our moon striking the Earth? Sure I can. Tricia Ferreira says, it looks like I'm going to start wearing a hard hat. And the Goblin's with us. Would an impact that size not change the Earth's day and night, etc.? It depends on how it strikes. But a glancing blow in the direction of our rotation could increase the speed of rotation slightly. And it could increase our speed in our orbit, at least temporarily, and that would make the orbit more elliptical, and that would change climate immeasurably over the course of time. But let's reset this. Let's go back to our solar system. There's hundreds of simulations that you can do here, but here we are, back to our solar system. First thing we'll do is go into view and go change the background so we just see stars. Right now, let me show you what the solar system really looks like. Okay, so we see all these nice trails, but we wouldn't see trails, and we'd see not just the trails, but we see names now, but we wouldn't see names. This is what we would see looking at our solar system from a distance. Okay, so that's the kind of thing that we would see. And that's what we see when we look at other stars. We just see clouds of debris around some stars like this. And from a distance, we might see a star in the middle and like a long kind of ring or a disk around the star. We do see it. We do see these types of things. Beta Pictoris is an example, okay, where we have seen this. Fomalhaut is another example where we've seen this, okay. But if you zoom in, you'll see that, where we see a disk like this big, we say, wow, we can see a disk around that star. We must be able to see like as far into the middle as we can. And the thing is, the star's size on our imagery is gigantic. It's bloating our image sensors. So we have to use a special tool called an occulting disk to block out the light of the star itself to see what's around the star itself. All right. In this case, if we look at our trails again, all right, we see that we would not see many of these inner planets at all. In fact, we wouldn't see any of them. And in fact, maybe not even the outer planets. However, we might see Neptune, okay? And we might see Uranus, but we wouldn't see these. We have done direct imaging where we had actually seen planets that are several times the distance of Neptune directly imaged. And that means all the way out here, kind of like the equivalent of Sedna's, but in the circular orbit. So that's the kind of resolution we have looking at solar systems, star systems that are in other locations now. But we do have our simulations in order to do this. And we have our sun. Now, let's get back to Johnny Pepper's idea. He says, let's hit the moon with the Earth, or vice versa. Good point. Let's do it. So let's go and grab the Earth. And let's zoom in. All right, here we go. All right. There's our Earth. And we are now moving at 18 days per second. Let's slow that down. Okay, let's go down to about 1 hour per second. And let's take our moon. Let's go get our moon. Here's our moon. And let's launch it into the Earth. Now we're gonna use the launch velocity that's slower. It's gonna be not 2.96. Let's change that. It'll be say 4 kilometers per second, because we have to account for the fact that something dislodged it and maybe accelerated it. Hey Raymond, thank you so much. Very kind. Good to see you again, Raymond, by the way. And so let's actually come down here, and now we're going to launch the moon. Now, first thing we're going to do is we're going to back out a little bit, and then we're going to do this. All right, so there's the moon. It's on its way, and I'm going to try to deliver a glancing blow. Let's see if I can deliver a... It's probably not going to deliver a glancing blow the first time around. I'll have to give that a shot, but we'll see. So here it comes. Uh-oh. I don't think we're going to be glancing at this one. I should have given it a higher launch velocity, because right now the Earth's gravity is overwhelming it. But that's okay. So the moon is big, and the moon has mass, and it's going to really do some serious damage. And if we add our graphs over here, you can see the impact occurring right now. So let's do that. Let's so here you see the compression wave, and the shock wave behind it is incandescent. Okay, so that is a shock wave that's several thousand degrees. All right, and it's going to rapidly overtake the Earth. And you watch now. We're doing 18 seconds per second. In real time, it's painfully slow. Okay, so here is about real time. Take a look at that. Those are actually in motion. Yeah. Okay, so let's go up to. This is 20 seconds per second. Compression wave is making its way all the way around the planet. And to people on the other side, they're like, what the heck happened? And then, boom, right there, pow. You'll notice that at this point, life on the planet has been extinguished. Okay, nearly all life. Everything on this side is dead. Okay, everything on this side is suffering burst lungs from overpressure, and of course, death from above. Raymond Bobel says, Elon, help! That's funny. But if we increase the speed, remember, this destruction is because of Donald Kunzer. He's the responsible for destroying the Earth. Just make sure you don't forget that. Donald. I think that's funny. Yeah. That's pretty good. Oh yeah. Meanwhile, if we back out, solar system looks fine. Things are still working. Donald Kunzer, space is big, really big. You just won't believe how big it is. And the rest of the quote is, if I recall, Earth is big, but that's just peanuts to space, something like that. That was Douglas Adams in Hitchhiker's Guide to the Galaxy. Trisha Ferreira says, cockroaches would find a way to survive. Yeah, maybe so. But let's just check this out. Okay, so the Earth is fully enveloped. Let's accelerate this and just see what the full extent would be. Wow, look at that. Earth has been reduced to a nearly molten state from all the impacts. So what happens is the atmosphere gets heated up tremendously. And that heating will be recognized when we look at the charts. Okay, the temperature now is 2,700 Celsius. Now 2,500 Celsius, dropping because it's now cooled off, but that's 4,000 Fahrenheit. Okay, so it's dropping. That's the high, and the low is a balmy 1,300 Fahrenheit. So Earth is dead at this point in this view. But this is actually characteristic of a time, one time when the Earth was in fact a molten state. So I think that's pretty cool. Michael Hedrick says, I go eat and the whole world blows up. Yes, sir. Why'd you go eat? It's your fault. No, actually, it's Donald Kunzer's fault. Donald is the one that wanted to see the Earth get destroyed by the moon. And, well, it did. So, yeah, this is quite a program. This is called Universe. Brain fart. Universe. Why am I? What the heck's wrong with my head? I'll get it. Okay. It's a program that it simulates the physics very well. It's called Universe Sandbox. Universe Sandbox 2. All right. The original one was good, but this one's actually better. Now, someone spoke about Betelgeuse earlier. So why don't we leave this behind because, of course, Earth is dead. And why don't we open up a simulation where Betelgeuse is where the sun is? check this out. Okay. Earth and all the planets that you know are inside Betelgeuse. All right. So Jupiter is also been eaten by Betelgeuse as well. Saturn's on its way in. Saturn is incandescent and nearly destroyed. We'll slow it down. The rings are certainly gone at this point. But here goes Saturn. Second biggest planet in our solar system. And no match for Betelgeuse. So if we accelerate this, as you can see, everything just starts going in because it's much higher gravitational forces. And before long, this area of space is empty of all life. And then you guys, blink, these are the last ones. Ooh, that one survived. That's Sedna. Look at that, guys. Sedna survived, at least initially. Yeah, it looks like Sedna's made itself into a stable orbit around Betelgeuse with some other little thing over there. Wow. That's pretty cool. Neat stuff. So let's try a couple things here. I'll show you. I want to, since we're now having some fun, what I'd like to show you is when the Andromeda Galaxy and our galaxy collide. Now, understand that this is a simulation showing the Andromeda Galaxy up above. It's got 1 trillion stars in it, and we have fewer, all right? And so in doing this, you'll see that the Milky Way and Andromeda, their cores are going to commingle. You see that right there? Those are the two black holes in the center of our galaxy and the center of Andromeda colliding and forming one. What this will do, is create a whole new galaxy of a very different kind. All right? So it'll take billions of years to stabilize. All right? So this is, we're approaching 1 billion years. Well, actually, 500 million years. And this will be the somewhat stable view. Now, it's still loading, so obviously it's actually overloaded. So what I'll do is I will exit from it and start it again. All right. Well, anyway, this is a lot of fun. And what I'll do is also, while we're waiting, hey, there's our chat. Let me go back to our chat for a second. And bring up our... That was our view from before. Let's say the live view. Kind of looks like Titan, doesn't it? Raymond, thank you, man. That's very kind of you. Lab fees, you're funny. Thank you so much, my friend. Ray is a staunch supporter of SkyTour livestream, as you guys can see. Done some very nice stuff for us in the past. He's, he does some really cool things. All right, so that's our view now. Right now, again, we're taking 8-second shots right now, so you'll see it get updated. And I might have another. Let's see what this time lapse looks like. I think this is the time lapse when the storm was rolling in, so you can see the clouds. Mm-hmm. Really something. Johnny Peppers, you're more than welcome. That was a great suggestion. So we can just punch ahead here and just see where we are. Yeah, here's the storm now with the rain hitting it. I left it out on purpose. It's still out there because I was testing its watertight nature, and I discovered that it's not quite fully watertight, but the leakage is it's just moist air that's getting in that's causing it to condense on the inside of the watertight box. And that's because I have a wire guide going in. It's called a gland, and it's got two wires going in, a cable for internet that you see here, and a cable for power. And you can tighten those down together only so much, and then you got to add like silicone sealer in there. But I have a few things to do before I do that. I've got to add a power supply in there. I need a 6-volt or a variable power supply that can go up to like 5.5 volts or 5.8 volts. And I've built variable power supplies before, but I don't want to do it again. There's the moon peeking through at night. It was snowing, as you can see. You'll notice the snow is melting. It was freezing out, but what I have is I have a setup where the heat of the processor itself, I'm actually circulating it within and using it to clear the lens that you see there. And it works. It's not enough to evaporate water because that requires a lot of power, but it's enough to melt snow. So I'm reusing the heat of the processor itself inside the box. Well, there we go. And then it's morning at 6:37 in the morning. And that was that guy. And let's see what this one looked like. Yeah, this is the full-on fog and really snowy conditions. This is way more humidity than we'll ever see in the Arizona desert. Way more. By probably 300% more, 400% more. So yeah, so we're good with that. Now I'm going to show you something else that it does too. And that's these weird things. Now it does star trails as well, which is kind of cool. So you can see there's your star trails from that one night. We had some clouds, but then we had some star trails, stars. And so it made star trails from Orion and from all the other clouds, or sorry, all the other stars that it rose. And if you just draw that logical line back to the center of the circle, it's out here somewhere, and that's where the North Pole is. Hey, James Hyatt. Welcome back. Good to see you. Yeah. So, you'll notice this is sort of blurry and fuzzy for this text, and that's because this is a conglomeration of many. Okay. So this guy, is this the one? Okay, these are called kilograms. In the beginning, you'll notice that it was bright and it was cloudy. Then the clouds cleared up, and here's the time in the bottom: 1800, 1920. So, okay, 6, 7, 8, 9, 10, 11. Midnight is here. Then 1, 2, 3, 4, 5, 6 in the morning. So you can see that during the night, around 2 in the morning, it was clear. 4 in the morning, 5 in the morning. A few clouds between 2 and 3, right? Clouds between 11 and midnight, right? But it was clear from 10 o'clock to 11 o'clock, clear from midnight to 1 a.m. See, so this is called a kilogram. Very, very useful to study trends in your weather. So I like this very much. They're boring to look at unless you know what you're looking at. Okay. All right. So that's said. Now let me go restart Universe Sandbox here. Because I'm not done playing. Are you? No, I'm not. All right. Cool. All right. We are back to our solar system. Okay. Once again, I'm going to go view and I'm going to say background, change it to only stars. I mean, we could change it to nebulae and all kinds of really cool stuff, you know, a really bright Milky Way, a dark Milky Way, blue, yellowy nebula kind of view, space blue. Now, about this view right here. Okay, this view is interesting because if you have been with me on other streams, you know that I talked about the Pleiades and their very, very interesting relationship to us, about 400 light years away, and they're going through a cloud of dust, and the blue light from the stars is being scattered, making the dust show to us. We can see the dust scattering this blue light from the stars. Well, there's some research indicating that that might be a vast cloud of dust, and we're in it. So this view of our solar system, although just notional, that is not real, but just suggested, might actually be realistic. So interesting. But we'll go to just stars for this. All right. Now we'll go back here to our beautiful sun. Now here's what we're going to do. You know, the sun ties everything together, doesn't it? So let's watch what happens if we remove the sun. Watch this. There goes the sun. And there goes the planets. It's like, hey guys, we're out of here. Bye. And then zing. Off they go. And they're just going to keep on going. The asteroid belt just heads on out into deep space. Everything else just keeps going. That's what happens without a sun. The fastest planets, Mercury and Venus, okay, followed by the Earth, they move the farthest, quickest. There they go. Now, another thing. If we replace the sun with a black hole, all right, and let me just restart this. If we replace the sun with a black hole, we would find that the sun is actually, the solar mass of the sun would not actually be something that would be changed, so therefore the planets would just continue to orbit around a dark star. Just wouldn't see it. All right? So I think that's pretty cool, you know? All right, let me show you a few things here. This, you can pull up lots and lots of stars. Okay, so here's our sun, right? That's our sun. How big is Rigel compared to our sun? Well, let's go get it. All right, look at the size of Rigel compared to our sun. It's massive. Massive. All right, so if I stop it and I just put it in there for a moment, okay, and then go down toward our sun, you can see the difference in size, right? Now you might say, well, what if you just let it go right now? What will we get? Well, Rigel's got a lot of gravity, right? Let's see. All right, and I'll reduce the time a little bit because I don't want to have it go so fast. Okay. So this is, I'm up to 1 day per second. All right, watch this. There goes Mercury. Ploof. Gone. Inside Rigel. And now the sun is approaching Rigel. Let's see what happens when the sun approaches Rigel. Will it destabilize Rigel? Boom. That's kind of funny. It's actually, I'll show you what I mean. That you see right there, that's actually not what would happen. Okay, Rigel and the sun colliding would probably disrupt either the sun or Rigel or both. So where this thing goes wrong, I can show you. Let's start up with a new simulation, and let's go back and say new empty simulation. Okay, let's go over here. Now let's add a star. What star? I don't know. Castor Geminorum. Let's add that star. There it is. Now let's add another star. All right, let's see if we can add Fomalhaut. All right, so you see Fomalhaut is a little bit smaller. And we're not going to orbit it. We're going to launch Fomalhaut at Castor Geminorum. All right, and that's what we're going to do. So let's get out of here a little bit, and let's launch it. And it's going to be 53 kilometers per second. All right. You see the solar flares coming off of Castor Geminorum. Fomalhaut C is being launched, so something's going to happen. We might see some magic occur right here. Let's see what happens. Whoa! How about that? The star actually looks to me like it became... it almost looks like it became some kind of a neutron star. But interesting. This version changes the way supernovas appear. I don't think that was supposed to be how it looks. But let me try that. Let me try generating a supernova. Let's open one. Let's see explosions. Exploding Jupiter. Okay, so this one. So this is how a supernova in the center of our solar system would expand outward. See? It's like being inside the Crab Nebula. And we increase the speed here. This is superheated gas too, so at this point, let's see if let's see how Earth would fare. I probably should have selected Earth before. Yeah, there's too many pieces of debris ahead of it. Well, let's try it again. Let me do this. We're going to start this again. Hang on. Let me go back to this. All right. And... okay. And stop it. Okay. There's Earth. Let's select Earth. Let's bring up its panel. Let's watch what happens. There's the supernova explosion. Let's Fahrenheit on this. Okay, that cloud is about to reach the Earth. If it does what it's supposed to. Hey, come on. just a second. I didn't want to do that. Just a minute, just a minute. Earth, right there. Oh, it's doing this to me again. Wait, there's Earth. Okay. Now let's go and... Okay, now we're focused on Earth. Now this material is going to reach the Earth. Let's see what happens. Uh-oh. Look at our temperature. Our temperature is climbing. So this hot gas is now reaching the Earth. It's pretty amazing considering that this is 2 minutes per second and the temperature on the Earth has risen 10-20 degrees in that amount of time. Now it's at 77, 90, I can't even say it, and more. So now you'll see that the Earth is now being superheated. There's the side that's exposed to it right there. So we're getting this superheated side of the Earth right there. And you'll notice that I saved us in the US. But you'll see that it's now it's serious. This hot material has reached us, and it's 3,000 degrees on one side. And if we look at our chart, we'll see that nobody saved anybody because the temperature is skyrocketing, 13,000 degrees, 7,000. It's literally astronomically higher temperature. Really bad. You'll notice also if we get up close, all right, you'll see that Earth is now shedding its atmosphere. Okay, that's what you're seeing here. Earth is shedding its atmosphere as the hot stuff reaches us, and the planet itself is being evaporated. That's what we're watching right here. Yeah, that's really makes me glad that we're not around the star that could go supernova. You know, Michael Hedrick says, brother wants to know what size of dwarf planet would be produced if all known asteroids were combined into one. I know the answer to that because I've done that. Believe it or not, if you add all of the asteroids together, all right, you get an object that's only the size of 1/4 of the moon. That's it. 1/4 of the moon. Now, if you add the dwarf planets that are out there, well, certainly we don't know. It's probably going to be a few more, certainly, but I don't believe that it'll get more than, say, half of the moon's size, maybe 3/4 of the moon's size. Eris and Sedna are the biggest ones we know of, and Sedna may be the largest, and we're not even sure exactly of its composition. If it's mostly ice, that doesn't really count as much as if it was rock. But everything has a certain amount of rock to it. Look at that. We are at 16,000 degrees in temperature right here, and still going higher. We are actually, we're in, now where's this stuff coming from? Well, if we move out, okay, you'll see that it's that hot blue center of the supernova that's evaporating our planet right here. Well, I don't want to get too close. You get burned. Okay. So that's pretty interesting. Here we're like 57,000 kilometers from it. Pretty cool, huh? That's really neat. So let's see. We've destroyed the planet with the Earth, with Apophis, with Vesta, and another one of the outer dwarf planets in the Kuiper Belt. And somewhere in this lonely galaxy is a tiny little star that's gone supernova. and nobody notices it. Except it's destroyed a planet full of life. So how many of these types of events have occurred in the universe? Could be a whole bunch. Hey, Ronald's here, Earth Radio. What's up, brother? Michael Hendrick says, does the density make a difference in temp? Absolutely. Density makes a very big difference in how an impact will occur. If you actually take a ice ball and send it into our atmosphere, you get a different heating process. You get thermal energy released because you're converting kinetic energy into heat, because the energy of motion coming to a stop in our atmosphere, the energy gets converted from motion to heat as it enters the atmosphere, starts to break up, and then when it hits, it will actually send immense amounts of stuff up into the atmosphere and then farther out into space. Look at this. The satellite for our gas pressure here is down now. Actually, I will just say that I'm kidding. I have no idea. So there you go. That's a neat process to see the Earth getting destroyed by a supernova. But oh yeah, look at that. That's crazy. I think Earth literally evaporated away. I think Earth is gone. We captured it just before it went and evaporated fully. Venus is evaporating now. Now, why didn't Venus evaporate quicker, being closer? Well, it has an atmosphere that's 90 times denser than ours. So I think that with an atmosphere that thick, you've got to evaporate all that atmosphere, and then you can evaporate the planet itself. So we don't see this anymore. If we zoom out, okay, you notice Mercury it doesn't exist anymore. Only Venus is there. And Venus is there, as I said, just because of the fact that it has a very, very thick atmosphere. 90 times the density of ours. So, and its temperature on the surface, however, is a balmy 16,500 degrees Fahrenheit. That's a lot higher than the 900 degrees Fahrenheit that it is. But the thickness of that atmosphere is keeping it alive right now. But it's going away. So this is why supernovae would be dangerous to life, because it'll do exactly sort of what we see here. It will cause planets to evaporate. It'll cause them to superheat, lose their atmospheres. The atmospheres go first. So I think that's pretty cool. So anyway, and I do want to, by the way, I just want to make a note, Jessica Smith, if you're still here, please make sure you subscribe. You're a new finder to SkyTour livestream, and you don't even get to see what we really do yet. Tell you what I will do though. I'm going to do an acquisition. Yeah, it's actually rained out there. That's too bad. I was hoping it would have cleared by now so I could do some shots with you. But let's see if I get rid of this guy. Yeah, that's there. I'll bring this back. I just did a all sky for the old all sky out there, and I noticed that it did rain. It wasn't rained. It had not rained earlier today, and I was hoping that it wouldn't rain and I could actually open up. So what I'm going to do right now is take us to 6 seconds. Save that change. go to preview, one acquisition, and then see what it looks like. So I'll let you know. Oh yeah. Okay, I think the rain is done, but we definitely have clouds covering the sky. Part of it's clear, part of it's cloudy. But with rain like this that's occurred out there, I'm not gonna put, you know, this much equipment at risk. Because what if the roof shorts out and doesn't shut? We're out of luck, because the nearest person is an hour and a half away, and that wouldn't be good. So we'll just live with that. Anyway, so let's now go back and let's try some other things here, because there is just so many things to do. Now, this next supernova that I'm going to show you, okay, this is you have a white dwarf, and the white dwarf is in a binary system, and material is leaking onto it. Okay, now a white dwarf can hold itself up as long as the mass of the white dwarf doesn't exceed 1.44 solar masses. That's a magic number. Beyond that, then the white dwarf will actually end up going into a supernova. This simulation shows a white dwarf here, okay, and this is material flowing onto the surface of the white dwarf. It's a simulation of that. So let's do that. There you see it. Okay, it gets to a certain point. All right, so far so good. Okay. So this star here is Sirius B. Okay, that's the one. It's the star that is a companion to Sirius, the main star. Okay. Now, this is not what's happening with it, but this is what could happen with it. So as material accretes, it reaches that magic 1.44 solar mass level, and then the next thing you know, the star cannot hold itself up anymore, because the process holding it up, the force, is called electron degeneracy pressure for the white dwarf, and it can't hold itself up once it reaches a certain amount of mass. So it starts to collapse again, but it can't collapse. All right, so because it's as compressed as it can get. So what happens? It literally implodes, and it explodes like this. This is called a Type 1A supernova. Now, the thing that's interesting about these supernovae that we're looking at right here, Type 1A supernovae are really important candles to us. They're distance candles. The thing is, when they explode at a certain point. Well, we know that certain point very accurately, and that accurate explosion point is the point where you'll see it be a certain brightness, and it's a certain brightness for whatever white dwarf it is, wherever it is in the galaxy. And so if we know its brightness, all right, we can then calculate the distance to it. So if it happens inside a galaxy, we'll know the distance very accurately to the galaxy. How's that work? Well, it looked like this. Okay, there are a couple of brightness characteristics of stars that we use. And I'm going to take a drink of water before I go into that. And that is this. We have an apparent magnitude, how bright it looks to our eye. So when I showed you that all-sky camera view of the stars, the apparent brightness of those stars is a value that we use. It's called a magnitude, an apparent magnitude. However, there's another brightness that we use, and that is the brightness of the star, no matter where it is, what it is, if we brought it to 10 parsecs away from the Earth. What's a parsec? A parsec is 3.26 light years. Okay, so if we brought it 32.6 light years away from the Earth, the brightness at that point, all right, is something called the absolute magnitude. And the absolute magnitude and the apparent magnitude are part of an equation that give us the distance to objects, okay? And I won't go into the whole equation, but understand that that absolute magnitude minus the apparent magnitude, that difference is called the distance modulus. And that value will give us the distance to objects. And when you have a supernova explosion like this one, okay, this supernova explosion is precisely the kind of explosion that occurs the same way every time. So when we watch an explosion like this occur, we are able to calculate how far away the object is because we know that thing called the distance modulus. We know the apparent brightness, and because white dwarfs are a certain brightness, we know how bright they are at 10 parsecs away, which is that absolute magnitude location. So comparing that brightness, we know how far away objects that explode in a supernova like this are. And how do we know that they exploded this way as a type 1a supernova? That's Roman numeral 1 with a little a after it. How do we know that they exploded that way? Well, we know that they exploded that way because of their spectrum. When we look at the spectra of a supernova, we can tell, oh, that's a type 2 core collapse supernova where the star just all imploded on itself. Okay? But this one is not. This type 1a supernova, they have different chemical abundances in their spectrum, which tells us that it's a type 1a supernova. So you get the spectrum. You figure out whether it's a type 1a supernova, which is a white dwarf supernova that's a binary with another companion feeding mass onto it, reaches that magic number and blows up, or it's a core collapse supernova, massive star that just runs out of fusion fuel of all kinds and then collapses on itself. Right? Whichever it is, we can tell the difference. And then if we know it's a 1A, we can tell the distance to that object. If it's in a galaxy, we know the distance to the galaxy. So these are called distance candles, and these distance candles are very important to us. We use them all the time. They're extremely important, and they form the fundamentals for understanding how far away things like this are in the whole universe. Okay, so that is the type 1a supernova and the type 2 supernovas. And so let's well, this might be interesting too. I think I've done this one. Okay, this is a completely fanciful simulation showing the Earth exploding with a moon that's like really, really close. Okay, and I'm going to show you something else about these in a moment, a little bit, the next one. But there's the Earth exploding, and you can hear the noise. It's pretty loud. Yes, indeed. Oh, yeah. We'll back away. Well, that just goes on and on. That's pretty cool. I gotta turn it down because you're hearing noise of the simulation here, but it's pretty cool. Neat. All right, now what I'm going to do is I'm going to take us back and I'm going to do a new simulation, and I'm going to show you what happens when the moon is too close to the Earth. Now, there was a point when the moon was formed where it was very close to the Earth. However, what ended up happening was that it was the moon formed at just the right distance so that the Earth wouldn't tear it apart. Beyond a certain distance, you end up getting differential gravity on the front face facing the planet versus the back face, okay, because it's so close. And what happens is the gravity will basically pull the front of the moon more than the back of the moon, and it will rip it apart. All right, and that limit, that location, is called the Roche limit. And outside of the Roche lobe, that area around the planet where it's a no-go zone, the moon could exist outside that Roche, around that Roche lobe. outside that Roche lobe. So let's go get the moon, and we're going to put it in, and we're going to just add it to our simulation, and we'll make it move a little bit too close to the Earth. And I want you to see what happens. Well, first I'll do this. First I'll move it out here. Okay, I'll add it right out here. Okay. All right. This is way closer. This is about how far away it was. Actually, if you saw the kilometers initially, this is about how far away it was when it was formed. Okay. And at that time, a day on Earth was about 8 hours long. Okay. And then because the moon was stealing momentum from the Earth, well, how does that happen? It's space. There's nothing between. But there's gravitational force. And because we have oceans, as the moon is going around the planet, right, if you look, the moon is tugging on the Earth. So it's tugging on the oceans and raising a tidal bulge. At the same time, at the other side, okay, or wherever the sun was at that time, it's raising a tidal bulge too. And those tidal bulges sticking out add friction to the rotation of the Earth. And as the Earth rotates, that tidal bulge kind of gets dragged forward a little bit. And now it's sort of at the leading edge of the Earth as it's rotating. And the moon, from its distance, sees that tidal bulge and the Earth. The tidal bulge has mass. It tugs an ever so small amount on the moon. And that tugging pulls the moon ahead just a little bit, a tiny bit, making it go a little bit faster in its orbit. And if you know anything about orbital mechanics and orbital dynamics, you'll know that when you tug something in its orbit and make it go a little faster in its orbit, it moves a little farther out from the object. So this is the reason that the moon is moving away from the Earth by about this much every year, 3 centimeters. Right? Because that tidal bulge is tugging it a little faster in its orbit. At the same time, because of the fact that the tidal bulge is ahead, as the Earth's rotating, that tidal bulge is pulled ahead a little bit of the rotating Earth. That adds friction to the Earth, and the moon tugging on that tidal bulge is starting to slow down the Earth a little bit. So the day on the Earth when the moon first formed, here, was around 8 hours. And then as the moon spiraled away and it was tugging on that tidal bulge, it slowed down the Earth. So instead of rotating as fast as it did, the Earth began to rotate slower and slower. Days became longer. 8-hour days became 10-hour days, became 15-hour days, became 18-hour days, became 23-hour, 56 minutes hour days like they are now. Right? And that's what happens when you have objects rotating and moving around each other. The moon is tidally locked to the Earth. It's close enough to be tidally locked because it was from day one, because it was too close. Later on, as the moon spirals away, what will end up happening way in the end of time, okay, is the Earth is rotating and it's slowing down, right? Well, you can project a time when the Earth may stop rotating. Well, it'll rotate, but it will be in sync with the moon, so that eventually Earth and moon will be tidally locked to each other, rotating around in space. And for the people on the moon side of the Earth, they'll always see the moon in their sky every single night. Astronomers will hate it. Okay? On the other side, it'll always be, again, tidally locked to the moon, but still the system will rotate as a whole. So what that rotation rate will be is, again, a mysterious conundrum right now. But the bottom line is that will cause the dark side of the Earth that's away from the moon, okay, to not ever see the moon again. And as an astronomer, that's the place I'll always go. I'll never have to worry about moons. I'd have all my remote telescopes on that side, and maybe one higher power one on the moon side so I could show the moon. Pretty cool. I want to welcome Alice Pooper. Hello there. Haven't seen you in a while. Good to see you. Of course, you haven't seen me in a while. I just checked the weather. It's cloudy out there, Alice, and so we're continuing with our cloudy night stream. So now that we have the moon in its early orbit, let's see what would happen if the moon had been any closer. So first things first, let's get rid of the moon, and let's add it back, but closer now. This is going to be a very close moon, all right? And let's see what happens to it. So far, you'll notice that something weird is happening. The moon is starting to break apart. What's going on? Well, that differential gravitational force that I told you about is affecting the moon. The side facing the Earth is being pulled harder than the side back there on the back side, and so the moon is getting torn apart. The consequence to the Earth is that it's getting struck by lots and lots and lots and lots of debris in extremely detrimental ways. Oh, there's a big one on the other side. Okay. So what this means is that if the moon had formed this much closer to the Earth, then the Earth would have been rendered incapable of generating life at any time in the future because of this problem we're seeing. All right, the moon will be within the Roche limit and inside the Roche lobe, and so it will end up being torn apart. And that's what we're seeing. Look at all the fragments. Where are those going to go? Well, they're all eventually going to spiral in and strike the Earth. Look at, see the fragments go all manner of ways. Watch this. Boom. See that? So let's speed it up and watch what happens. You notice that we started with the Earth stationary in space, and it ended up being pushed away from all the collisions. There we go. Wow. So the Earth is very hot. Temperature is 4,500 C, and in terms of Fahrenheit, we're talking about 5,200 degrees, 7,000 degrees Fahrenheit. And then eventually they'll start cooling. All right. So if we keep going long enough, the system will stabilize. Okay. So now we have a stable system with a moon that is small enough that it's not going to be subjected to being ripped apart. You notice the moon's a lot smaller. And so now this is a really interesting setup. You notice we have one fragment over here. Okay, the question was arisen earlier when the moon was formed. Okay, or at least does the Earth have more than one moon? This is one way in which it could have happened. The moon could have been a lot closer and bigger and got ripped apart and then stabilized in its orbit further out, and one fragment kept going away and moving in a far off strange orbit. This could be we could be looking right now. This could be the system that was created where we have a fragment that became a small moon of the Earth right there, right? Because we do have one like that that's orbiting the Earth right now. Then the regular moon, and then the Earth. Now multiply this by billions of years, and we have our Earth back. We have the tidal bulge formed. We have the moon spiraling away. So here, where a day might have been 4 hours long initially or whatever, it's now going to be something else. And it's going to get longer and longer and longer. So this is kind of cool. The physics shows well. The only trouble is when you accelerate this, the program takes shortcuts, and you'll actually you cause inaccuracies to ramp in, and we don't like that. But for showing you, it's actually pretty cool. All right, so let's check out one of the other sets of collisions. We can be silly, okay? All right. So this is gonna be slow because it's 100 cows moving at the speed of light, and that's probably gonna cause me to have to abort because that's too fast. I should have slowed it way down. My mistake. All right, but that's kind of cool. Now, how about an Earth and Mars collision? This is one that's interesting because now the collision speed here is probably too high, right? And it's going to be a direct collision. It's not going to be a collision like that would create the moon. I'm actually working on a simulation like that where I can actually show the Earth, show a collision with a Mars-sized body. I think it's called Theia. And you see fragments break off. Earth has a ring for a period of time, and they coalesce to form one large object, and that would be the moon. I got close. I actually got that to happen like one time. Well, the problem is I get impatient. I want to see it, so I hit the accelerator, and when I hit the accelerator, it gets inaccurate. So what I'm going to do now is I'm going to slow us down. So this is basically just about a minute per second. Okay, this will be 2 minutes per second. 2.5, 3. This will be 3 minutes per second. All right, then I'll slow it way down as soon as we get into Earth's. Okay, this is 17 seconds per minute. Oh, that's death. Yeah, that's absolute death. That's just not good. You see shockwaves moving away here. Massive large asteroid-sized chunks of this impactor. This type of thing actually happened in our solar system when it was forming. Cosmic Ray, I don't know what you mean with your question. So you see, a Mars-sized body that would strike the Earth would, of course, result in a shock wave that reached around to the other side in no time, and boom. At that point, overpressure would have literally exploded the lungs of any living creature on the planet. And luckily at that time, there probably weren't any. Yeah, but, you know, this is the kind of thing that happens. I have no idea what just happened. I didn't tell Earth to go supernova. Oh, I'm sorry. I might have hit a key that said explode. Yes, there is a key where you can do an explosion. You can also do some interesting things here. For instance, you can make different materials. So in other words, you can have materials like you go to tools, say material. And now you say water. You can spray the moon with water, okay, and see what happens. Okay, let me slow it down a little bit. All right, and just come in here. So you can spray the moon with water. All right, and have lots and lots of water appear in the moon and then watch it evaporate. Okay, so there it is. And now I've got a nitrogen planet showing up, and it's going to strike the moon. And when it strikes the moon, it's going to spread nitrogen all over the moon. Shockwave after shockwave. What's interesting, after this is done, all right, we'll let this go. You'll actually see the moon is reshaped by this impact. Okay, there's the crater left by the nitrogen. You're seeing nitrogen ices. That's what this is. These are nitrogen ices that are all over the moon's surface. Now, anytime something strikes the moon at this point, let's suppose we take an asteroid. Let's do a minor planet of some size. Let's say Ceres. No, Ceres is pretty big. Let's see the Swift-Tuttle comet. No. Vesta again? Yeah, maybe Vesta will work. And we'll launch Vesta at the moon. Okay, that was quite a hit. And you saw something happen right there. I ended up going too fast. But let's do it again. Alright, we'll let just the nitrogen thing hit. We'll let it make the nitrogen ices. There we go. Okay, nitrogen ices. Notice the color is a little different because the water ice mixed with it made it a little bit different. Okay, so now let's go back and let's hit it with, let's see. Well, we'll try something small. Let's try Deimos first. And this will be about 1 kilometer per second. Let's increase this to like 5 kilometers per second. Impact speed. And we'll slow us way down here. That was a little too fast. Okay, let's try that. There we go. Deimos. You'll see it go in there in just a minute. There it goes. Yeah. Let's watch what happens. This will be Mars satellite Deimos hitting a nitrogen-laden moon, a nitrogen ice-laden moon. Here we go. Oh, look at that. Nice splash. Really cool. That's really neat. And this side of the moon has less nitrogen on it because this was the impact side. So let's go here. Let's launch something else. Launching stuff is fun. Universe Sandbox 2 is available. You can get this on Steam, or I think you can get it separately as well. So I think you should try that. You have fun with it. It's a really cool product. Now let's do this. Let's try. Let's go to moons. How about Mimas? Yeah, Mimas is pretty big. Let's see though. Well, let's do this. Okay. Mimas. Yeah. Speed it up. Speed it up. Mimas is around Saturn. And, of course, Mimas has a radius of only 198 kilometers. But still, that's actually a significant size, especially at these collision energies. Let's watch this happen now. Goodbye. Oh, look at that. Wow. Ooh, looks like an eye. You will listen to me. You can see the shock waves. You see those ripples, the shock waves with those things struck, like right there. When they hit, they leave shock rings. You see that? That's really, really cool the way that happens. Excellent shock waves. And of course, that was where Mimas struck. And they circled the moon several times. Well, this is cool. And I've got to say, like I said, Universe Sandbox 2, it's available on Steam. It is a real, real cool program. You can do all kinds of really neat things. It comes with a few things. Now, there's a lot of historical ones, too. And, like, for instance, Asteroid 2019... okay. This was an asteroid that was detected just hours before it actually passed by the Earth. And there it is. If you look, that's a near-Earth asteroid. It literally passed right by within the orbit of the moon. That's actually, that's pretty close, right? Now, if we actually pause this for a minute and just pull out to the point where we can actually grab the asteroid, take a look at this asteroid. Look at its properties. We're getting here right now. Okay. One more time. There we are. Right. So if you look, the radius of this little tiny asteroid, 3.78 centimeters. Now, I don't know. To me, that doesn't look like very much. It's not really, obviously. It's like, 3.7 times 10 to the minus 5 kilometers. So it's really, really tiny. As far as meters, it's only, 0.04 of a meter in size. So it's small. But if it's moving fast, it can do significant damage if it struck the Earth. Okay, hey Sean, thanks, man. It's so nice of you to come by. Yeah, Skywarden, right? Let's keep all the asteroids away from the Earth, huh? Well, it's actually not a bad thing, because what I could do is I come up into tools, and I can say, oh yeah, all right. Well, maybe what we can do is explode this guy, right? And let's do that. Watch, here we go. Let's zoom in. This asteroid, you pass close to us. No soup for you. No soup for you. And let's pull out of there. And boom. Okay. Now it's just a pile of rubble. There we go. And boom. Of course, I had it on pause. So there we go. So let's do one of these other ones. Remember the Parker Solar Probe? Parker Solar Probe was really fascinating. That probe went right near the sun. It's still heading toward the sun. And it's going to take up this orbit where it's going to actually park itself and be circling ever closer to the sun. And so it doesn't look like it's that close, does it? But it is very close. So, you know, it reads August 12, 2018, NASA launched it. It was it was really meant to study the sun's corona, the outer atmosphere, the thing that shines outside the disk of the sun there. And it will study the wind, the solar wind that's coming from the sun. All right. Now, this is a shield that could protect it from the radiation. So it's really cool. So it actually has flown by Venus several times in order to get closer and closer to the sun. And it's not really powered in any way. It was only sent up to orbit with rockets, but once it got into its orbit, we're letting gravity do the work for us. The gravity of Venus, the gravity of the sun. And so these gravity assist type flights are a study in mathematical analysis to get it just right. And the fact that we could land ourselves on a little asteroid called Bennu out there without any problem shows that we can really target an area quite well. There was when the asteroid Bennu was touched down upon by the OSIRIS-REx probe, it touched down, grabbed a sample of the asteroid, brought it back, let it go over the Earth into the Earth's atmosphere where it was collected out in the desert, and it continued to another asteroid. And so it's actually saying, here, drop off on my way to another place. I mean, the fact is we can do some pretty amazing things. We can really do some pretty amazing things. Let's go to pull this away a little bit so you can see where the Parker Solar Probe is going. Okay, there's Mercury. Another near pass right there. And let's go back and see. Now it's pretty far. See that? Yeah. But you can see where it's going to go. I mean, it went here, and now it's using... It's gone by Venus several times in order to get closer and closer and closer. And the orbit has been translated closer to the sun. Every time it passes through the corona, we get data. And that's pretty cool. But we're not at the point where we can just park and hold. You know, we don't have that kind of Star Trek capability, unfortunately. But there's our Parker probe. There you go, that black shield protecting the sun, that it looks at the sun on the way back. Not bad. Notice the Pleiades right there. Right there. Not bad. Okay. So that's pretty cool. And there's dozens of historic simulations you can check out, you know. But anyway, there we go. So that is Universe Sandbox, and that is our evening stream for tonight. It's just a really pretty simulation that is probably among the best. And I'm pretty impressed with how it works. Let's go see this one. One more. Remember, always one more. Okay, the Zwicky Transient Facility found Comet 2022 E3, which we observed, if you recall. And this comet is right here. And it's coming in. And as it gets closer to the sun, it will then outgas and do its outgassing. I'm not sure how the program handles the outgassing, or if it does. The green color is due to a number of chemical compounds that are created at the surface of the comet. One of them is cyanide, It's a carbon atom and a nitrogen atom. And when a carbon and nitrogen atom are bonded to each other, that is cyanide, otherwise known as cyanogen. And so that's what we see. And then this nucleus becomes very excitable when it gets close to the sun, and it starts to outgas and give off gases and things that end up trailing behind it. And like I said, I'm not sure if we're going to actually see a comet tail here or not. Maybe not. I mean, with all the other capabilities, it should be able to show it. It would already be showing it if it could. Well, that's the view from the comet, heading away from the sun. So it leaves the land of the living and goes into the land of the cold. Pretty cool. Neat. So it says right here, they colored it green artificially to show the green light given off, but Universe Sandbox does not simulate the physical mechanisms that lead to the emission of that. And it's true, the surface of the comet in reality is probably black or dark gray. That's what we have noticed actually and seen. Very cool. James Dugan, how you doing? Izabela, thank you for putting out some very helpful messages in the chat. Thank you very much. Okay, let's see. It's like I don't want to stop, but I know I have to. Okay, this is a good one. I've seen this one before. If you wonder what a solar eclipse looks like from space, okay, this is cool. So check it out. We're going to play it. All right. And you're going to notice a shadow. There it is. Okay. What is that's the shadow of the moon out there. And it's passing, see the moon? It's going to pass in front of the sun. Well, there it already did, I guess. But see that is pretty cool. So this is a total solar eclipse. This actually is moving across this way. This was 2017, August 21st, total solar eclipse. But sometimes, you see, like I said, when the moon and its crossing of the plane of the orbit, that precessing orbit, when it reaches the spot between Earth and Sun, we'll see a solar eclipse. When it reaches the spot between the Earth, if you draw a line through the Sun and the Earth, okay, where it would be directly behind the Earth compared to the Sun, then we'll get a lunar eclipse. And that's where, again, it's the descending node, okay, has to be right crossing the plane of the solar system, because that whole thing precesses and spins slowly around. Pretty cool. Well, very cool, actually. Exceedingly cool. The neatest thing I've ever seen. Okay. Oh, there's just too many. Just too many. But since we looked at Shoemaker-Levy striking Earth, let's take a look at Shoemaker-Levy striking Jupiter. Okay. We'll slow it down a little bit, just enough so you can see the particles. Okay. So here comes Shoemaker-Levy. Right. Now Jupiter's gravity, boom. Jupiter's gravity broke it apart. Okay. And as we watch, each fragment striking Jupiter It has the energy of many nuclear bombs. You imagine that striking Earth. You saw what happens to Earth with Apophis, right? Now, one thing I don't see are the scars on Jupiter from the impacts. Quite a lot of fragments, though, I'll tell you that. Yeah, we're done now. I don't see the scars from the impacts. That's all right. You see the trajectory and the physics is correct. That's what I like about it. Oh, Izabela says, can you take us into a globular cluster tonight? Oh, I probably could. Not in this application, though. I do have another application that I would use for that. And let me see if I can get that running. Because if I can, then yeah, why not? Because it's really cool. All right. So there we go. Let's go see our cam. What I want to see is our camera. See what our camera looks like right now. So let's hop out of here. Let's get out of the screen thing. And now we're in our webcam. All sky cam, I mean. And let's see what the live view looks like. All right. Well, no precipitation, a little bit, but we're still getting clouds. You just saw it change there. Still rainy here. Again, kind of looks like Venus or Titan. All right. Okay, so what we'll do is we're going to get out of Universe Sandbox and move ourselves over somewhere else. And why not, right? A few minutes in this won't hurt anything. So let's go in here. Let me set this up. All right. We'll have to do that. All right, let's do this. All right. I'm going to set us up to do this now. Let's do this and say we're going to capture, not that. One second. I want to grab our application here. This is what we got to do. Let me do it this way. I think it's this one. Add new source. All right, and let's do the window. There we go. That looks like that should do it. That looks like it should do it. And don't forget me. All right. Okay, let's go into Space Engine and load up. This is our view of the moon in Space Engine, and it's really, really quite accurate.